Alright, so let's look at this problem. It's a little bit different than the one we just looked at. It's the same idea in that it's a kind of a nice one-bay, one-story frame. It's got some horizontal force. It's got a concentrated load. So what's the first step in all these problems, probably? Yeah, let's find the reactions. I'm going to cheat a little bit and use my original drawing as my free body diagram for that, just to save a little space. So when I do that, at A, I'm going to assume that I have a force in the y direction and a force in the x direction. And then, since this is a roller, I'll just have a reaction force, vertical. I'll assume it's dy, and that'll be up. I'm going to come over to my distributed load here, which has an intensity of 3 kips per foot. And it's over the height of this column, which is 12. So base times height of the triangle gives me 36. So I'm going to have an equivalent force of 36 kips acting halfway up, which will be at 6 feet. That should be enough to help me solve for AX, AY, and DY. Like we've done many times before, I'll start by summing moments somewhere. You could actually sum moments at A or D. I think either one will be productive, but I'll do the traditional one of summing at the pin. So let's sum moments at A, and then make sure we're in equilibrium. And again, I'm using right-hand rule for my sign condition. So about A, both of our applied forces create what kind of moment about A using right-hand rule? Positive or negative? Negative. So I'll start with the concentrated equivalent first. So that's 36 kips. And the distance from A to the centroid is 6 feet. And then the concentrated load, which was 15 kips, that's the force. And the distance from A, its line of action, the distance is 4. And then the last thing is my reaction here at dy. What kind of moment does that create about A? Positive. So that'll be the unknown dy times this distance, which looks like to be 8. So what is dy? 34.5. Anybody else get 34.5? 34.5 kips. And it's positive. That seems reasonable. About A, you can see both these forces would cause the structure to try to rotate clockwise. So the reaction force is pushing against that. So that makes sense. Now we can come and find our other reaction, AY, by summing forces in the y direction, making sure it's in equilibrium. So AY and dy are both up. So in my sign convention, those are positive. In the y direction, this is in the x direction, so I don't have to worry about that, but that 15 kip force is down, so it'll be negative 15. So what is the reaction at AY? Looks like it's going to be negative. Whatever, I don't know, that minus, what is it? 19.5. 19.5? We talked about one of these earlier, that if you get enough big horizontal force, your structure will try to rotate to the right, so this reaction at A is not just holding the structure up and falling, it's actually holding it down and flying away. That makes sense. And then the last one, we will sum forces in the x direction. And there we have AX to the right, that's positive in my sign convention. And we have the concentrated equivalent, which is also to the right, so that'll be positive 36. So it looks like that AX is going to be negative 36. So we found our reactions. So now we need to find what's happening around the connection B and C. So this is where we're going to take it apart. We're going to end up having to take apart and look at section AB, BC, and CD. So this is almost the same as the problem we just worked. So I think you can see that I can take it apart here at AB, what I have to deal with. If you look over here at CD, that one's going to be pretty easy to handle. And then really the in-between, the beam, the BC is not going to be very difficult. This is just the one load. So there's a lot of different ways to approach it. I think what I'll do is I'll just start with CD, because I think that's going to be an easy one. And then I'll just come over here and do BC and get my reactions at B and C, and then we'll draw the diagram.
AB or BC?
What did I say?
So BCs.
I think I'll do AB and CD. There's really, unlike our previous problem, these two are pretty close. Once you get C, so we'll have the C in, then you could do BC if you wanted to. I kind of like to avoid that if possible, because if I do mess up CD, which is unlikely, but it's possible, then that information would go in here and affect my answers for B. Whereas I go over here to AB, I'm not bringing in other results. It's the same idea we had in trust analysis. You don't have to bring in previous answers. Why? Why do it? Why risk the possibility of infecting your new solutions with bad solutions? Okay, so I'll start here, and we'll do CD. So I'll draw the element CD. Now we've already found what dy was. It was 34.5. It was positive. I assumed up, so that means that this is going to be a force of 34.5 kips acting up. This is 12 feet. And now I'm going to just make some directions. I'm going to say this is CX. This is CY. And that's my moment in C.
And we can assume these directions.
Any way you like. Now, when we take these results and we start drawing the shear force and bending moment diagram, then you got to go back and use the shear force and bending moment diagram sign convention.
Does it really matter which moment you picked for that?
And doubly so in this problem, because when we're going to sum moments at C, you're going to find out there is no moment at C, so it doesn't really matter. And we'll do that now. So if I do sum moments, and usually it's a good idea to sum moments at that cut that you just made. We've done this a few times. We've done it for trust analysis and for writing our equations for shear force and bending moment. So at the cut surface, this moment would be a positive moment in my sign convention. CX and CY create no moment about the cut, and of course the only force on the whole system is axial through it, so there's nothing. That's it. That's a pretty easy equation to write and solve for. I think you probably saw that coming.
So we leave out AX and that distributed load because they cancel each other out. Is that right?
Well, we're looking at just CD.
Oh, I'm sorry. Yeah. Thank you.
So if we sum forces in the y direction, I've got CY acting up, and then I've got this 34.5 kip force acting also up. So it looks that CY is negative 34.5 kips. So we do know now that CD is in what? Tension or compression? Compression. Are we drawing compression force diagrams? Not at this time. So we really don't need it. The only thing that would cause shear would be CX. And I think if you quickly look at it, you'll see that if I sum forces in the x direction and make sure it's in equilibrium, all I have is CX. So there is no shear and there is no moment in CD. Again, that's going to be a pretty easy one to draw. Now I'll come over and look at the free body diagram of just section AB. So I'll draw that one. Let's see what's happening here. It's 12 feet tall. It does have a distributed load applied on the side. and that has an intensity of 3 kips per foot. At A, we solve for AY. It was down. That's 19.5 kips. We solve for AX. We assume to the right it's negative, so it's in this direction. And that's 36 kips. And then I'm going to go up to B, and I'm going to assume BX, BY, and a moment. And I'm not really concerned whether they're shear forces or bending moments. I'm just saying, hey, my sign convention usually is X is to the right, Y is up, and my moment is right-hand rule. That's the only thing you got to do. So I do have 3 unknowns in this free body, so I can do the same thing we did here. I'll sum moments at the cut. In this case, that cut is at B, and make sure it's in equilibrium. So with right-hand rule sign convention, this moment is positive. To handle the distributed load, just like we did at the beginning, we're going to use the concentrated equivalent form of this, which we've already solved for, which is just base times height, which is 36 kips. And from B, it'll be 6 feet away, half the distance. That 36 creates what kind of moment about B, positive or negative? Positive. So force is 36 kips. Moment arm is 6 feet. We know BX and BY create no moment about the cut. How about the 19.5? No, it's axial. It passes right through B. So just this 36 force down here, which was our AX force, does it create positive or negative moment about B? Negative. So that would be a force of 36 kips and a moment arm of 12 feet. So what is the moment at B? 116, and it will be positive. Now, when we draw our shear moment diagram in a minute, we'll find out whether this is going to be a positive or negative bending moment. But right now, that's the correct direction. Okay, so we can now sum forces in the y direction. Make sure it's in equilibrium. What do we have going on in the y direction? Well, I've got this by is up. What else? What else? Oh, this is down at the reaction, minus 19.5. So it looks like I can solve for by. Be positive 19.5. So section AB is in axial compression or tension? Tension. Again, we're not doing axial diagrams, so we don't have to worry about it, but it is in tension. But we do need to know the x value. That will give us some information on the shear here. So I'll sum forces in the x direction, make sure it's equal to 0. So I've got bx to the right, positive. I've got this 36 to the right, positive. I've got this 36 to the left, negative. So what's bx? 0. So in this case, our column is not transferring any, we've got no shear here. Okay? So that's just the work needed to get the data so that we can now draw the diagrams, which was the original part of the problem. And we are 14 minutes into this problem. Good to know, huh? By the way, these are your homework problems for the weekend, so you got plenty of time over the weekend. I mean, I'm sure after Memphis Madness tonight, you'll be fully recovered tomorrow, and you'll head into the weekend strong and ready to roll. I'm going to do it at Memphis Madness. I'm going to have an interesting challenge next week, and I'm going to need your help. My wife is leaving town Saturday. She's got to go visit her dad in Barry's Bay, Canada. I think it's snowing there. I'm going to be without any adult help with 3 small children for 10 days.
How many days?
And
Wow.
so if I show up Tuesday, have pity. Don't make it bad. Make it good. Make it good. Bring me a candy or. Speaking of candy, I read this morning that most common artificial sweeteners kill the gut bacteria in rats. And that's not really that surprising to me. That's like, if you put a nail gun next to your head and pull the trigger, you might put a nail in your brain. So it's one of those like duh studies. Yeah, if you put foreign chemicals into your body, it might kill something in there. Something that you might want to keep. Somebody paid for that too. Probably us. Okay, enough of that. That was very political. I shouldn't have said that. I take that back. I retract the previous statement. I'm just saying that officially because the man is listening. So let's do A and B. Let's start with drawing the diagram phrase. So this is what's cool about this is I can literally rotate it for you. So that's the way you can draw it now. So now it's clear to see that this force now becomes the shear force. So I'm just going to put this off to the side and I'm going to draw it that way. I think I might be able to squeeze it in here. So there's the beam. It's got a distributed load on it. Right, we've done that already. I think we've handled distributed loads. That was 3 kips per foot. The height of my is 11. Now I'm looking at the 8x force, and we got 36. So I think it was 36 in this direction. Our result for bx was 0, so nothing's happening there. We had no moment at A, but we did calculate a moment at B. Right? And it was in this direction, it was positive. So again, if I rotate it, you can see now if I'm drawing my beam in this direction, what kind of bending moment would that be? Positive. So that means I know I'm going to have a positive bending moment at this end equal to 216. So that's all the data I need to go. So I'll just go ahead and draw my template. I'll come here and define a positive x-axis, positive value for my shear. All my values will be in kips. What is the shear at A? Positive 36. We also know what? We know that the change in shear is the area under the load curve. Have you heard that before?
Yes.
Good. And then what is the area under the load curve? It's a rectangle. Base times height. 36. Positive or negative?
Negative.
Excellent. So it goes to 0. 36 minus 36 is 0. We also know that the slope of the shear diagram is given by the value of the load. And what is the value of the load everywhere? Negative 3. So this curve, although it doesn't look like it, has a slope of negative 3. In fact, somebody might ask you that one day. What is the slope of the shear diagram between A and B?
Maybe that one day is next Thursday.
Yeah. So now what do we do? Moment. So let's start with a positive x-axis for moment. For the x and the positive moment. All of our units will be in kip feet. What's the moment at A? 0. What is the bending moment at B? Positive 216. Can we connect those dots? I hope so. We know that the change in moment is the area under what? Shear curve. What's the area under our shear curve? 1/2 base times height.
That would be 216.
That would be positive 216. So 0 plus 216 gives you 216. Excellent. And then the slope of the moment diagram is equal to the value of the shear. What is the value of the shear at A? Positive 36. And it drops to 0. That might not be a bad question to ask, too. What is the slope of the moment diagram at A? Positive 36. And then connect those things with a parabolic section, and there's your moment. One down, 2 to go. So now we'll do the next section, which is from B to C. Now from B to C, there's a load applied right in the middle. It's 15 kips. And that's at 4 feet and 4 feet. Now we already know what's happening at B, right? We know our moment at B is in this direction, equal and opposite, right? And has a value of 216. Let me flip back to here for just a second. So at B we found BY. Did we solve for BY? We did. It was positive, so it was up. So that means BY on section BC is do I have to talk about that again? So here's section AB. We found that at A it was down, so BY was up. So that's in tension, right? So how does this force transfer to BY on section BC? Is it going to be up or down? Down. And what's the value? What about CY? What's happened over at C? Well, we solved for CY, right? And we found out that it was negative, so it's actually down, which means it's up. And what is it equal to? I think that's everything. So let's draw our template. There's my left side. There's my right side. 15 is a point of interest. I'll put one in for there. So we'll start with our shear. There's our positive x-axis, positive shear. Everything will be in kips. What is the shear force at B in BC? What kind of shear force is that? Negative. So we're going to start off at negative 19.5. The change in shear is equal to the load. The load is nothing, so it's going to stay there. Shape is equal to the load. The load is 0, so that's a horizontal line. So it's just a step, constant shear. Now as I go from the left side to the right side, how does my shear change?
Drops 15.
Drops 15. What's 19.5 minus 15?
Negative 34.5.
Wow. You guys done this before? The change in shear of the last 4 feet is given by the area in the load curve. Area in the load curve is 0. Mr. Frizzell, what is the shear force at B on section, at C on section BC?
Negative 34.5.
Excellent. And the load is 0, so the slope is 0, and there you go. Now what? Now we do our moment. Positive x, positive moment. All of our units will be in kip feet. What is the bending moment at B? 216. What is the bending moment at C? 0. Let's see if we can make those connect. So the change in moment is the area in the shear diagram. What is the area in this part of the shear diagram? 4 times 19.5. What is that? What is it? Subtract that from 216. What do you get? And what's the slope of that line? Well, it's given by the value of the shear. So that slope should be what? Negative 19.5. What's the change over the last 4 feet? Should be the area of this curve, which is base 4 times height negative 34.5. What is that?
138.
Oh, that's amazing how that works out. So 138 minus 138 is 0. And what is the slope of this curve? Negative 34. So it is steeper. So I'm trying to draw it somewhat to a scale. There you go. What's the maximum moment in the frame? Yeah, where does it occur? What's the maximum shear in the frame? 36. Where does it occur? Like that. All right. Any other questions about this? We'll work some more of these, and you'll get a chance to work some over the weekend. All right.